Is about the mean value theorem. So hopefully you watched the Rolle's theorem video first. And really, the Rolle's theorem is actually just a special case of the mean value theorem. So in this case, we can do a little bit more general. Now with the Rolle's theorem, we had to have the same y value. And in that case, then there was some place in between the 2 points that would make the derivative 0. So this is a little bit more generalized, that basically if we think about, so this is the slope here. So I have this graph. It's y equals the square root of x, just for your, and I'm just looking at it between 1 and 9. And what mean value theorem basically says that so I calculated the slope, you can kind of see here. So basically 3 minus 1 over 9 minus 1, and I get 0.25. So then I wrote the equation that would go through those 2 points and with that slope. And essentially, this isn't my tangent line, right? Even though it kind of looks, it's the point slope form. This is a line, this is the secant line that hits 1, 1 and 9, 3, okay? Now the slope of this line we just calculated was 0.25. Now what the mean value theorem says is that essentially the slope of this line doesn't have to be 0. The slope of this line can be anything. And as long as my graph is connected in a continuous and differentiable way, then somewhere along here, I'm going to end up with a tangent line that is parallel to my secant line, meaning that the slope of this secant line will be the same, that the derivative will take on the same point at some place between 1 and 9. So if you just kind of look at, so I've got like oh wait, I got to put it on there first. So the red one is my original function. The black one is my slope of my secant line. I'm going to take away the red one because it's a little bit easier. So essentially now remember, so this is my original graph, right? And the purple one, if we look at it, actually let me play it here real quick and leave that on there. But the purple one, it's going to show like the tangent line as it moves along, right? There. So what I'm looking for is what this mean value theorem basically says is that somewhere between x equals 1 and x equals 9, the slope of my tangent line will be equal to the slope of this line, which means visually they'll show up as parallel. So if I take away the actual function and just look at the two, right, somewhere we passed it right in there, right, it looks like it's parallel. So let's stop it here and let's see if we can actually figure out where that is. So somewhere, hold on, can I drag this point? Oh, that's actually that point. Okay, so let's move this essentially back here to about, no, that's not quite it, right? Because they're definitely going to cross. So if I move it maybe back a little bit more, does that go the right way? There we go. So essentially that's looking, it's hard to tell exactly, but that's looking approximately in the parallel. Like it's really difficult to see like exactly where it is, but we're definitely in the ball. Now that's definitely not parallel, but sort of like in here, it's definitely close in there, right? So essentially, if I put this back on here, right, you can see that it is tangent to the curve. It's looking like about 4. So what the mean value theorem basically says that if I calculate the slope between my 2 points, right, so I did that here, 3 minus 1 over 9 minus 1, and I got essentially 1/4 or 0.25, that somewhere in between x is 1 and x equals 9, that I'll find that my derivative is equal to 1/4. My derivative will be 1/4 for some x value between 1 and 9. And from what I'm seeing here, it kind of looks like it's about 4. Okay, so let's actually work it out algebraically. Okay, so we have the official stating of the mean value theorem that if f of x is continuous on the closed interval, meaning the endpoints are included for a, b, and differentiable on the open, so that means it can be not differentiable on the endpoints, but it has to be continuous on the endpoints, then there exists some value c such that x equals a and x equals b, such that f prime of c is equal to, essentially, this is just the form This is the slope of the two, right, of the between the 2 points. So this is the slope of the secant line. This is like the old way of calculating slope where y1 minus y2 equals x1 over x2, right? This is the same thing, just written in our functional notation, that there's some place that slope between the 2 points is equal to the derivative somewhere between a and b. Or alternatively, this book particularly likes this form, which is exactly the same thing. It's just I'm multiplying both sides of my equation by b minus a. So this is the same form. It's just a little bit algebraically altered. So the one that we were looking at online when we were looking at the graph was the square root of x between 1 and 9. And we already did, essentially, but I'll just redo it here for a second. So the slope between my line is f of 9 minus f of 1, right, all over 9 minus 1. Okay, and we calculated that on Desmos, and we ended up with 1/4 or 0.25. So just to do the quick calculation here, f of 9 would be 3 minus 1 over 8, which gives me 2 over 8, which is 1/4, right, which is also, right, 0.25, but you know how I like my fractions instead. Okay, so that means what I want to show, now what we could see graphically is we thought it was about when x was about 4, where I ended up with a slope of 0.25, where it looked parallel. So my f prime of x is, so this would be x to the 1/2, just a reminder. So my derivative would be, right, so this is f, that's just a rewrite, so f prime of x would be 1/2 x to the negative 1/2. And so since I'm going to try to put numbers in it, I'm going to write it as 1 over 2. Negative 1/2 means I have the square root of x in the denominator. So that's my f prime of x. Now I want to know where this is equal to 1/4. So I'm actually going to use the 4th because I think it's a little bit more useful in this case. So I want to know where is this derivative equal to 1/4. So I'm going to set 1/4 equal to 1 over 2 square root of x. And in this case, my fraction works for me here because, like, if I have this, right, if I have a half equals a half, then when I roll it over, I have 2 equals 2. So basically, the reciprocals will still be equal to each other. So I'm just going to flip this equation upside down, both of these. So this would be 4 equals 2 square root of x, right? Because the 1's become in the denominator, and then they're just, we just really don't need them anymore. So to solve for the square root of x, we divide both sides by 2, and we end up with the square root of x is equal to 2. So to get rid of my square root, I'm going to square both sides, and I get x is equal to 4. And now I proved algebraically what I could see on the graphically, right? So now we know that f prime of 4 is equal to 1/4. So that finishes off my mean value theorem, right? So I basically just did the slope between these 2 points, right? Just basic back to pre-calculus slope, right? So basically the y, I plugged in 9, I get y is 3 here. This one I plugged in 1, I get y equals 1 here, right? And then I just subtract 9 minus 1 in the bottom. So this is not the derivative, this is just me calculating the slope. But then my mean value theorem says that as long as my function is continuous, and when we looked at the graph of this one, and differentiable, which it is, then there should be some value of x between x is 1 and x is 9, such that I'm going to get the same slope as the slope of my secant line. And I showed that in this case. I found the derivative, I set it equal to the slope that I found over here, and I found that at x equals 4, I get this. So this is my, I've shown that it does in fact apply, and I found my c value, okay? So let's do that again. So we're going to find the c that satisfies the mean value theorem. So this is y equals x cubed, a completely continuous and differentiable polynomial, so we don't need to really worry about that too much. So let's calculate first. So again, we're going to find, we're going to find some f prime of c that's equal to essentially f of 3 minus f of negative 2 all over 3 minus negative 2, right? That's just my slope formula, my basic slope. Okay, so f of 3, I plug in 3 here. F of 3 is going to give me 27, right? And then f of negative 2, I plug in negative 2 here, and I'm going to get negative 8, so I have really minus negative 8, which is plus 8. And then in the denominator, I have 3 minus negative 2, which is really 3 plus 2, which is 5. So now on top, I have 35 over 5, which is equal to 7. So the slope, right, so basically, I know that, just a quick sketch here, right, that y cubed, or x cubed, I'm sorry, looks like this, right? And so if I have negative 2, let's see, negative 8 is somewhere down here, and then I have 3, 27, that's way up here, right? If I connect these two, right, then this, I found that this slope is 7. So now we want to find an x value that falls between negative 2 and 3 such that it also is equal to 7. So we find our derivative. So that's where we need to find f prime first before we can figure out what c value will make it equal to 7. So I have my y prime is equal to 3x squared. And now I want to know where this is equal to 7. So 7 is equal to 3x squared. So since I just have a plain x squared, I'm just going to solve for it. So I get 7/3 equals x squared, and I'm going to get x equals plus and minus the square root of 7/3. Now, I actually think both of these might be in between here. Hold on, let me, yeah, so when I approximate the square root of 7/3, this is approximately plus or minus 1.53. And so basically, actually, both of these will fall in between negative 2 and 3. So I actually found two different calculations that was true. So basically, I found that f prime of the square root, actually, I'll just write it like that, thirds is equal to 7. And I also found that f prime of negative square root of 7/3 is equal to 7. So the whole thing should be in square root, sorry there. So let's do another one like that then. So, of course, we can't leave out the trig. So let's look at y equals the cosine of x minus the sine of x. So we want to show that the mean value theorem will work, right? Cosine and sine are both continuous functions, and so when we combine them, that should also be continuous, so I shouldn't have an issue with that. So let's calculate the slope. So that's f of 2 pi minus f of 0 all over 2 pi minus 0. So on the bottom, I know I'm going to get 2 pi. So then if we plug in, let's say we do y of 2 pi here, then cosine of 2 pi is 1, and sine of 2 pi is 0, so that would be 1. And actually, y of 0 falls exactly at the same place as 2 pi, so I'm going to get 1 minus 1 in the top, and actually I'm going to end up with 0, which really, this is technically speaking Rolle's theorem, right? Because we found that the slope between these two lines is horizontal, and so technically we have Rolle's theorem, which is just a very specific case of the mean value theorem. So we can still use whichever we'd like to call it at the time. So I guess we'll call it the Rolle's version of mean value theorem. And so we need to find y prime and find out, hopefully there's some value that we'll find between 0 and 2 pi, where the derivative of this is equal then to 0, because that's the slope that we calculated here. So y prime is the derivative of cosine is negative sine of x, and the derivative of sine is cosine, so I have both of them negative. Okay, so this time I want it to be equal to 0, so I'm going to put 0 over here. All right, so since I have the plus and, I have addition between them, I'm going to move the sine to the other side, because I can kind of see that if I divide them by cosine, I'm going to have tangent, and that's kind of what I want. So I'm going to add sine to this side, so I get sine of x equals negative cosine of x, and then I'm going to divide both sides by cosine. So I have cosine of x, I'm going to leave the negative over there. So I get tangent of x is equal to negative 1. Okay, so we're trying to remember our unit circle again. So where is the tangent of x equal to negative 1 between 0 and 2 pi, right? Again, on our interval. And we know that the tangent of x is 1 at multiples of pi over 4, right? And since I want it to be negative 1, then that would mean I would want to be in the second and fourth quadrants, right? So that means I would want, let's see, the second quadrant would be 3 pi over 4, because, right, it's bigger than, slightly less than pi would put me in the second quadrant, and then the fourth quadrant would be slightly less than 2 pi, which would be 7 pi over 4. And we do want to call them these. This isn't like the arc, right, because this one we gave between 0 and 2 pi, so we want these angles to be between 0 and 2 pi. All right, so we found that 3 pi over 4 and 7 pi over 4 will give us a tangent of -1. And so I found I get 2 possible. Remember, Rolls and MBT say that there's at least 1, and so we actually found 2. So we found that f prime of 3 pi over 4 will be 0, and also f prime of 7 pi over 4 will also give me 0. And just to double check in case you doubt, right? So pi over 4 is 1 over the square root of 2, 1 over the square root of 2, right? And so 3 pi over 4 means I'm in the second quadrant where basically cosine would be negative, right? So that would be, I would have essentially negative square root of 1 over 2. So that would be plus 1 over the square root of 2. And then sine of 3 pi over 2 is positive, right? So that would be actually negative because the negative's already there, 1 over the square root of 2. So then that gives me 0. So there you go. And then if I had 7 pi over 4, then these would be opposite, right? This time, this one would be the -1. Actually, it would be the sign that would be the -1. So it would be this one that would be negative. So that's the sign. So then I'd have negative sign. So I'd have actually positive 1 over the square root of 2. And then this one will be minus 1 over the square root of 2. So then this one also gives me 0, just in case you didn't believe me. Okay? So I showed that this one actually has 2 places. All right, so one more. A little bit more algebraically complicated. So this time we're going to need to use the quotient rule when we find our derivative. So just to find the slope of the secant line that joins 1 and 4, right? The point 1 something, right? It's actually 1 f of 1 and 4 f of 4, right? So we just need to calculate the slope between those. The slope between those are, I just go with the biggest one first. It doesn't matter if you use f of 1 first as long as you use 1 first in the denominator. So I'll do f of 4 minus f of 1 all over 4 minus 1. All right, so I know in the bottom I'm going to get 3. So y of 4 will be 4 over 4 plus 2, which is 4 over 6, which I'll simplify to 2/3. So that's 2/3 here. And then y of 1 is going to give me 1 over 1 plus 2, which is 1/3. So I have this so far. So I have a little bit of a compound fraction going. Good news is the numerator has a common denominator. So my m is really 2/3 minus 1/3 on top, which is 1/3 over 3. And then if I multiply the top and the bottom by 1/3 to make 1 in the denominator here, I'm going to get my slope is 1/9. So now we want to find where is the derivative of this equal to 1/9, right? Hopefully I'm going to find a value between 1 and 4. So my y prime, this time I need the quotient rule, so it's the bottom, so x plus 2, times the derivative of the top, which is just 1 in this case, minus the top times the derivative of the bottom, which is also 1, all over x plus 2 quantity squared, just an application of my quotient rule. So this is going to give me then x plus 2 minus x over x plus 2 quantity squared, and my x's are going to cancel and leave me with 2 over x plus 2 quantity squared. In this case, I want to clean it up because I'm going to set it equal to something. So now I want to know where is this equal to the slope of my secant line. So I have 2 over x plus 2 quantity squared equals 1 over 9. So I'm just taking my cleaned up derivative and setting it equal to the slope we calculated above. And now I have, in this case, I have a fraction equal to a fraction. So this is one of the few cases where I can cross multiply. So I'm going to have 2 times 9, which is 18, equals 1 times this, which is x plus 2 quantity squared. And now We're going way back to algebra here, so we can take the square root of both sides here. When I do that, I put plus minus, of course. And so I get plus and minus the square root of 18 equals x plus 2. And I can move the 2 to the other side, so I get, I'm going to write it in this direction. X equals, this will be negative 2 plus or minus the square root of 18. Now I am between 1 and 4. And I can see that if I look at these separately, negative 2 minus the square root of 18 and negative 2 plus the square root of 18, this one is not going to be between 1 and 4 because this is negative, and then I'm going to subtract even something more negative from it, and so that's definitely not going to get me an x between x equals 1 and 4. So let's look at this one, and I put that in my calculator and decimal approximate it, and I get that x is approximately, let's see, 2.242, which is good because that does in fact fall between our original up here, 1 and 4. So we found that really f of, sorry, this screen isn't very big here, f of negative 2 plus the square root of 18, I'm just going to leave it in its original form, is equal to 1/9. And if I really, really want to check that, right, I can do one more thing here. So let's come back up here to my f prime, right? So my f prime, let me rewrite it here, was this 2 over the square root of x, or actually 2 plus x plus 2 quantity squared. So I'm going to have that. And so just to check it out, I'm going to do f prime of, actually I should have left a prime symbol up there, f prime of negative 2 plus the square root of 18 is equal to 2 over, now this is my x, negative 2 plus the square root of 18, and then plus 2 down here, quantity squared, which is equal to 2 over, these cancel inside and leave me with the square root of 18 quantity squared, which is really 2 over 18. And when I simplify it, I do in fact get my 1/9. And so my value here, which is approximately equal to 2.242, does in fact fall between 1 and 4 and satisfies my premise of the mean value theorem.